So far, we've spent a lot of time with graphing rationals, which required that we talked about vertical asymptotes and horizontal asymptotes. And then most recently, we did a little bit with solving rational equations. But one thing you may be missing from our class is how does this apply to my daily life? So don't worry, I got you covered. It's now time for applications of rational equations. Applications, of course, are what make math meaningful. So I'm only going to pick on one context to play around with. There are so many different ways we could look at applications of rationals, but I thought the idea of distance, rate, and time would be a fun one because it's something that's tangible and relatable. So you guys actually already know the relationship between these three quantities, right? If you've driven around or ride a bike or take a bus or anything, there are calculations we all do to figure out, how long is it going to take me to get from here to there and that sort of thing. So the kind of base relationship between these quantities could be expressed as if I multiply my rate by my time, I'll get my distance, right? So that's basically how we think about it. So if I'm going 50 miles an hour, that would be a rate, and I travel at that rate for 3 hours, I would get 150 miles as my distance. And what's cool about the math is that the units actually work out. So if I have 50, we typically write miles per hour as mph, but I'm going to write it as miles per hour this way so that you see the units cancel a little better. And then I'll show timesing by those 3 hours. So this is just nice visual for seeing how hours would cancel because they're top and bottom. And then the 50 times 3 gives the 150, and then the unit of miles remains. So that's just kind of neat, right? That's the relationship between those three quantities. Now, of course, we don't always want to calculate distance, right? Sometimes we know our distance and our rate and we want to find time. Or maybe we know our distance and our time and we want to find our rate. So we can very simply manipulate this formula to generate two other relationships. So if I go ahead and divide distance equals rate times time by, let's say, time on both sides, I'll find that rate is equal to distance over time. So again, all I just did there to come up with that form was I divided both sides by time, which canceled out time on one side, left rate by itself, and now rate is equal to distance divided by time. So that could be handy. And let's see, there's one more form, right? You could figure out the missing form would be, what if I want to get time by itself? So we're just taking turns getting this formula for D equals, for R equals, and now for T equals. And to get T by itself, I would want to divide both sides by R. So we can say that time is distance over rate. And if you plug in actual numbers, you will see that it works really, really well. So for example, let me just take away my scribbles there. So if I traveled 100 miles in 2 hours, 100 miles in 2 hours, that would be an application of this formula because 100 miles divided by 2 hours reduces to 50 miles per hour, and that would be a way to find the rate. If I told you I went 100 miles and I was driving 25 miles per hour, I would find that it took me 4 hours to get there, right? So just wanted to make sure that feels super practical and super comfortable before I even dive into how it looks in our math class. So this is just talking about a nice practical formula here. All right, so these three little things I'm going to bubble off and say, hey, these are different ways to express this relationship depending upon what we're looking for and what we're given. So you guys ready for an example in our class? Let's go ahead and try it out in a little bit more algebraic context. So let's say I'm going to use a canal, right? We have a lot of canals in Phoenix. So let's say that a canal is determined to have a current, so it's flowing. We do get some flowing water around monsoon season. And let's just say it's 3 miles per hour, so nothing super, super crazy. And let's say that I've got a boat I'm going to put in it. Actually, I'll make it my friend's boat, so it's easy to talk about. Let's just say I want to find the speed of my friend Amy. I want to find the speed of Amy's boat in still water. So assuming there wasn't a current, how fast could her boat go? If I know that she's able to go 16 miles downstream. So in the canal, she goes 16 miles with the current, right? Downstream would be understood to be with the current. In the same time that it would take her to go 12 miles upstream. So you can see that if I'm traveling against the current, I don't go as far, right? That kind of makes sense. So think about, any moving water you've seen. If you are floating or in a boat in the direction the water is flowing, right, you're going to go a little faster. And then if you're trying to go upstream, you can't go quite as fast. This is a lot of information, so if you feel overwhelmed, it's okay. That's pretty normal with word problems. So a general approach to any word problem is to first just read through it. Read through it so much that you could look away from the page or the screen and be like, this is what's happening, this is what I know. So you really want to read for understanding. For me, this often takes, maybe reading it two or three times, and then maybe even drawing a picture. So sometimes the other thing I do with problems like this that helps me is I make a little chart. And you can take this idea or leave this idea. But I know there are 3 quantities we talked about on the last page, and those were distance, rate, and time. So I want to see if I can incorporate those into our discussion here, distance, rate, and time. And then I know there are both a downstream consideration that we have here and an upstream. So let's see what we know for sure, and let's see if we can figure out what we're finding and what we should call it. So this part takes a little bit of time, so just stick with it. So the current is 3 miles per hour for the canal's water, the water that's flowing. And I'm not totally concerned about that 3 by itself, but I'm concerned about how it impacts the speed of Amy's boat. I do know some distances, so maybe that's something I can throw in our table right away. We know she goes 16 miles downstream in the same amount of time, that's going to be another key phrase that I can't forget, that it takes for her to go 12 miles upstream. So at least those 16 numbers and those 12 numbers, those can be placed immediately in my chart to organize the information. I also know that whatever time ends up being here, it will be exactly equal to the time that goes here. So kind of what I'm thinking about is if I can find a way to describe the rate downstream, and if I can figure out a way to describe the rate upstream, we can use the relationship we talked about on the previous page, which was that time is equal to distance over rate, and that will allow me to fill in these last little blocks here. So let's consider our rate for a moment. If we're in a boat, the boat has a speed of its own, right? Whether it's you rowing or if you happen to have a motor on it. And then the current will either speed you up from that existing boat speed, we could call it the speed of the boat in still water. You'll either get speeded up by the current if you're going with the current, which is downstream, or if you're going against the current, then it's going to slow you down. The thing is, in this problem, we don't actually know how fast the boat goes. The question is, find the speed of Amy's boat in still water. So whenever I see a find or a question mark, that helps me know what my variable should be. So in math, we need to pick a variable. Typically, we use x. But if I let x be the speed of Amy's boat in still water, then I'll be able to do something with x to generate a downstream rate and an upstream rate. So this is going to be the speed of the boat in still water. Okay, so I know both of these rates will involve Amy's boat, but now I need to play around with what we know about the current. So the current is 3 miles per hour. If I'm traveling downstream, would it be fair to you guys to say I'm going to be sped up by that amount? So it's however fast I go and then plus that speed. Whereas if I'm going upstream, that current is actually going to slow me down. So you can see that adding 3 to the downstream makes the rate here faster than the rate upstream where I'm subtracting. So just be a little careful with which one you're adding and which one you're subtracting. So in case it helps, downstream again is with the current and upstream is against the current. Okay, cool, just laying some foundation. So after this, we're all going to want to go and jump in a boat, right? So now that I have my chart filled in, mostly, I can use this relationship of time equals distance over rate, and I can fill in that last block. If you need to pause for a moment and kind of make sure you feel good on our setup so far, please do so for sure. But I'm going to start filling in the time for downstream as the distance down, which is 16, divided by the rate down, which we described as x plus 3. So that would be a symbolic representation for time. Of course, that doesn't feel like an actual number yet. It's just the symbolic representation. For upstream, it would be the distance upstream, which was 12, divided by the rate upstream, which was x minus 3. Cool. So now our chart is fully filled in. And maybe you want to walk away from the problem and say, come on, that's enough, right? But we still haven't answered the question. So in my mind, this is all just a part of the setup process. If it feels a little tedious or a little long, the thing is, if your setup is good, your solving should be good. So spending time on the setup is not a bad thing. Now, the only thing that's left to do is solve. So in order to solve, I'm going to make use of this one important phrase here that says the same time. So the time it takes to go down is equal to the time it takes to go up. And we have a symbolic representation for both of those. So I'm just going to write an equation in words that says time downstream equals time upstream. And then I'll fill that in with our symbolic representation for each. So we had stated a moment ago that time up could be expressed as 16 over x plus 3. Time down could be expressed as 12 over x minus 3. And what do you know? We have a nice rational equation, right? Now, we all solve things differently, so feel free to just do your algebra dance from here, whatever you're comfortable with. I'm going to go ahead and cross multiply. I'm a big fan of cross multiplying. So I would get 16 times x minus 3 is equal to 12 times x plus 3. And you could reduce by a factor on both sides. I'll just go ahead and distribute because I think that would be an intuitive next step. So if I distribute on both sides, I'll get 16x minus 48 on the left side. I'll get a 12x plus 36 on the right. I know I got to get all my x's on one side, so from here I'm going to show moving my 12x over to the left side. And I'm running out of space here, so I'm going to try to just keep squeezing it in. Sorry about that. So 16 minus 12 would give me 4x minus 48 equals 36. And from there, let's see, a next step could be to move the 48 to the right side, so I'm isolating x on one side. So that means I've got a 4x on the left equaling, let's see, what's that give us? 84 on the right. So if I divide both sides by 4, we will have the value for x, which we can remember what that stands for. So I think 84 divided by 4 should give us 21. And 21 is the value of x, and x stood for the speed of Amy's boat in still water. And that's the question that we were asked in this problem. So the boat that Amy's in is going 21 miles per hour in the canal. 21 miles without the current impacting it, 21 miles per hour. So I ran out of space there. So I'm just going to write a little sentence to interpret what we found. So Amy's boat goes 21 miles per hour in still water. When she's going downstream, her boat's going to be faster than that. When she goes upstream, her boat's going to be slower than that. So we've probably got a little motorboat on our hands. So hopefully that's kind of interesting to you guys. This is a fun application. It could apply to driving in a car or flying in a plane, right? In a plane, you would have wind traveling with or against the wind. So look forward to a couple more like this in the days to come.